Today I want to begin a topic called the radioactivity, but before we do that, we have to define something called isotope notation. It's just a way of describing a different isotope or a different version of an element. Every element has a symbol, like carbon, for instance, is a symbol C. There are two numbers that we use that are associated with carbon. There's what we call the atomic number, which for carbon is number 6. And it represents the number of protons. So if you're asked how many protons does carbon have, well, it's 6. How do you know that? You look on your periodic table, find the atomic number, and see that it's 6 and say that it has 6 protons. The other number that we have to do in physics 30 is what we call the mass number. Now, the mass number for carbon can vary. The atomic number can't. If the atomic number changes, it isn't carbon anymore. If the mass number changes, it is carbon. It's just a different isotope or a different version of carbon. You can have carbon 12, you can have carbon 14. They both have an atomic number of 6. This is what we call the mass number, and it represents the number of protons plus the number of neutrons. So in this example, I should say, we'd have 6 protons, but we'd also have 6 neutrons. If we have 6 protons and 12 protons and neutrons, then there must be 12 minus 6 equals 6 neutrons. If we had, let's say, carbon 14, which we could easily have, then it would be 6 protons. Still, carbon always has 6 protons, but we would have 8 neutrons. 14 minus 6 is 8, right? How many of you guys are familiar with this notation already from chemistry class? Okay, probably if you've taken chemistry, you'll be familiar with it. Okay, we use this, but understand that there's slightly different forms of this as well. You might see something written like this, carbon 14. Don't give you the atomic number. Where do you get the atomic number from? Periodic table. Right? If you're not told what the 6 is, you can get it from the periodic table. You always need the 14 because the 14 is different depending upon which isotope you have. But the 6 is always the same, and we can always get that from the periodic table. Another way you may see this written is something like this. Again, the mass number is 14. Good. The atomic number, don't know what it is right now, but we can look it up on our periodic table. Find that it's 6. All right. Now, why do we learn about isotope notation? Because when we study this new concept of radioactivity, it sometimes becomes a very important notation that we end up using when studying it. Radioactivity is a natural process. It's a random process. Radioactivity happens on its own, and it happens when it wants to happen. We don't control it. We can't even predict it for a particular atom or a particular nucleus. Now we can make predictions based on statistics. Like I say, I go to flip a coin. What are the odds of me flipping heads? Well, 50%. But I can't predict whether it's going to turn up heads or tails, can I? Yeah, I can make predictions based on odds, based on statistics, but I don't know whether it's going to turn up heads or tails. Same thing with radioactivity. We can make predictions based on statistics, but for individual nucleuses, we don't know what's going to happen because it's a natural process and it's a random process. What is it? It's a phenomenon where one nucleus decays into something else. Carbon becomes nitrogen. Uranium becomes thorium. Element X becomes element Y. It's alchemy, right? You're changing one atom into another atom, which in chemistry class, you pretty much learn can't happen. Physics, hey, we're more powerful than those chemists. Okay, we can make this happen. Well, not really, actually, because it's happening naturally and randomly. We're not making it happen. But it can happen according to the laws of physics. No, that's not the case at all. It's just that chemistry doesn't normally touch upon this because chemistry deals with the atom and the electrons surrounding the atom, right? Everything you do in chemistry ultimately comes down to electrons, sharing electrons, swapping electrons, whatever, right? We're not talking about electrons here now. We're talking about the nucleus. And that's just not a branch of chemistry. So in chemistry, they say, well, you can't change carbon into something else. Well, that's because using chemical means you can't. But under other circumstances, it can actually happen. The resulting radiation is called ionizing. What's an ion? What's an ion, somebody? We're going to say that an ion is a charged atom, positive or negative, a charged ion, or sorry, charged atom. Now, what's produced as a result of radioactivity isn't an ion. What's caused as a result of radioactivity can ionize atoms, can turn atoms into ions. Now, you always hear that radioactivity is bad for you. Well, a lot of times it is bad for you. Why? Well, if you happen to ingest these radioactive particles that can turn atoms into ions, then all of a sudden we get ions floating around inside our body that aren't supposed to be there. And then we get chemical reactions taking place inside our body that aren't supposed to take place. And then we get bad things happening inside our bodies that aren't supposed to happen because we get these chemical reactions that aren't supposed to happen. We get things like cataracts in our eyes, radiation poisoning, sometimes mild, sometimes severe. We get cancer can develop from radioactive poisoning. Sometimes death happens if the radiation poisoning is severe enough within a very, very short period of time. All kinds of crazy things can happen because these ions cause chemical reactions that aren't supposed to happen. And then they do funny things to our body as a result of that. Yep.